In the third chapter, we will study the climb performance, and the first mini lecture is about the climb angle or the angle of climb. Once the aircraft have achieved the screen height, basically means when the takeoff has finished, two performance parameters need to be considered in the climb phase. So the first is climb angle. Climb angle is crucial to avoid the high terrain or buildings close to the airfield. And you can see on the lower side of this slide, and this is how the climb angle is defined. The climb angle is also important to minimize the noise disturbance on the ground because, for example, in the Heathrow Airport, it's very close to the residential area, and the climb angle need to be considered to avoid the noise disturbance to the residents. And also there is another parameter, climb gradient, and when we talk about the climb angle. So climb gradient is actually the climb angle in percentage. So it's defined as a ratio between changing height and horizontal distance traveled. The second parameter is climb rate. Climb rate is important for the aircraft to reach the optimum cruise altitude and speed in an efficient manner. So climb angle and climb rate are the two important performance parameters when we are investigating the climb performance. And in this mini lecture, we will focus on the climb angle. Now let's first have a look how to calculate the climb angle. And we have an aircraft during the flight in the flight path showing on the right hand side. And we are looking at two directions. One is along the flight path, the other is normal to the flight path. Along the flight path, so we have the thrust, the drag, and also a component contribution from the weight of the aircraft. So that's W times sine theta. And normal to the flight path, there is lift and also the contribution of weight W times cosine theta. Now we're focusing on the direction along the flight path, and dv over dt is the aircraft acceleration along the flight path. And if we assume it is steady climb, so dv over dt is 0. Okay, so the equation along the flight path can be simplified as w times sine theta equals thrust minus the drag. Okay, so we can further write theta explicitly. It's arc sine t minus d over w. So this is a flight path angle. And if we assume the angle of attack is small, which means the climb angle equals the flight path angle, so gamma equals theta, then we can calculate the climb angle is arc sine t minus d over the weight w. Okay, so this definition of climb angle is based on the assumption of steady climb and a small angle of attack, two assumptions applied. And in the bracket, t minus d over weight w is named the excess thrust to weight ratio. And there is a very important or extreme case, t minus d over w is equals 1. And this gives the climb angle theta, which means the aircraft can climb vertically, but normally t minus d over w is far less than 1 for typical aircrafts. If the aircraft can really have gamma equals 90 degrees. Really, it has really high maneuverability. It's likely the fighter aircrafts. We've already derived the climb angle. It can be calculated as arc sine t minus d divided by the weight w. Then we have a question. Is there a maximum climb angle? It now all comes back to the equation t minus d divided by w. We know during the climb phase, although there is a fuel consumption, the weight is nearly constant. So if we have a maximum t minus d, the excess thrust, then there is a maximum climb angle. So we know the thrust decreases with the speed of air. If we look at this graph, we should know the thrust decreases. And regarding the drag, it has induced drag and a parasitic drag. We can see according to the graph here, although we will show how we can get this graph, the induced drag decreases with air speed, but the parasitic drag increases with speed. And there's cross point between the induced drag and the parasitic drag at a certain point. Okay, so we can find there is a point we have the maximum excess thrust available. So that's T minus D. That's a gap between the thrust available curve and the total drag curve. So if the gap is the largest, which means we have a maximum T minus D. Okay, so now let's have a better look. Okay, so let's first define the minimum drag velocity V minimum. At this speed, the parasitic drag and induced drag are the same, have the same magnitude, and the total drag is a minimum. We can see the conclusion from the graph below, and I will demonstrate this through an example later. And the second is the speed for maximum angle of a climb, Vx, and usually Vx is smaller than V minimum, and when the aircraft is climbing at the maximum climb angle, which means the total drag is not the smallest, and you can see from this graph. Now we have a question. If the thrust does not change with airspeed, let's compare Vx and V minimum. I give you a few seconds to consider. Okay, you can see from the graph the thrust decreases with airspeed, and we have Vx smaller than V minimum. Then it asks if the thrust is a constant. Actually, it can be assumed like this, and we have assumed this earlier in the example. And what happens to the Vx and the V minimum? The answer is V minimum equals Vx. Now let's see an example. How can we calculate the climb angle, climb gradient, and the best angle of climb speed Vx, the minimum drag for the aircraft, and the maximum climb angle for the aircraft. So basically all the quantities we've discussed earlier. So let's first read through the question. An aircraft is in a steady climb. The mass of the aircraft is 175.7 tons. The wing platform area is 286.5 meters square. The drag polar CD equals 0.015 plus 0.0576 CL square. So this is drag polar is actually comprised of the parasitic drag and the induced drag. 0.015 is a parasitic drag coefficient, and the second part is induced drag coefficient because it's related with lift generation, CL. The total climb thrust from all engines at 315 knots is 260 kilonewton, so we assume the thrust is constant. Through the use of small throttle pushes, it may be assumed that the thrust remains constant for the range of speeds and altitudes. If the aircraft is flying with a true airspeed of 315 knots at an altitude where ambient pressure is 89.9 kilopascal and a temperature of 282 Kelvin. So calculate the climb angle, climb gradient, best angle of climb speed Vx, the minimum drag for the aircraft, the maximum climb angle for the aircraft. So 5 parameters to be calculated. Okay, now let's see how can we solve this problem. We know the pressure at the altitude is 89.9 kilopascal, the temperature 282 Kelvin. So we need to first determine the altitude and the air density from the International Standard Atmosphere. So part of the ISA table is showing, and the range of the data is between altitude of 750 and 1000 as highlighted in here. So we need to do the interpolation, that's linear interpolation, and we can get the density of 1.1165 kilogram per meter cube. So this is a density at that altitude. And okay, so now let's first calculate the climb angle, which is x sine t minus d divided by w. And we already know the thrust is constant of 260 kilonewton, and the weight can be calculated as mg. It becomes 1721.86 kilonewton. And the question now is, how do we get the drag? We have the drag polar, and inside the drag polar we have CL. So first of all, we need to get the lift coefficient, and because it's a steady climb, so CL equals L divided by half rho v squared times S, and L is equals the weight, and this is assumed um, the climb angle is a small angle, so we have the CL is 0.41. Okay, then based on that, we have the drag polar CD equals 0.015 plus 0.0576 CL square. Then we can have the CD drag coefficient, and then we can have the total drag, which is about 1.3.8 kilonewton. And finally, we can calculate the climb angle, which is 5.2 degree, and it is a small angle. The second is climb gradient. As explained earlier, climb gradient is actually the climb angle expressed in percentage. And how can we uh, express angle in percentage? Let's see how can we do it. And gamma is a climb angle, and we've calculated as arc sine 0.091, which is the ratio between a fourth triangle, and eventually it's 5.2 degree of the climb angle. And actually the climb gradient is just 9.1%, which is based on the fourth triangle. So that's the climb gradient. And the third is to calculate the best angle climb speed, which is Vx. So we have the drag polar, and which is comprised of the parasitic drag and the induced drag. And so we can make a graph based on the parameters we achieved. So the red curve is a parasitic drag, and the blue curve is the induced drag. So the parasitic drag increases with true air speed, while the induced drag reduces with true air speed. So the total drag is the addition of these two, parasitic drag and induced drag. And according to the previous observations, we know the minimum drag velocity happens at a cross point between the parasitic drag and the induced drag. And according to this graph, it happens at tree at a speed of 145.29 meter per second. And at that moment, the total drag is the smallest. And this is actually the minimum drag velocity because now the thrust is constant. So the maximum climb angle speed, which is Vx, equals V minimum. So Vx is 145.29 meter per second. This is based on the graphical method. And based on the theory, so we can equal dp and di. So we have CL, we can get the CL. So from the lift equals the weight based on a small climb angle assumption. And then we can have the Vx is exactly the same as from the graphical method. So this also in return demonstrates the theory when the parasitic drag equals induced drag, we have the minimum drag. The fourth parameter to be calculated is minimum drag during climb. That's when the aircraft is flying at V minimum. Okay, so we have CD minimum, which is 2 times the parasitic drag, because anyway, the parasitic drag equals induced drag. So we have the minimum drag coefficient, and we know the minimum drag velocity, which is based on the Vx. So finally, we know the minimum drag is 101 kilonewton. The last parameter is the maximum climb angle. So and it's quite straightforward now. We can just use d minimum in the equation. So finally, we have the maximum climb angle is 5.3 degree, which is very close to the current climb angle, 5.2 degree.